And what if I told you that in the emptiest space we can imagine, where not even a single atom exists, there is still something? And what's more, that something could contain enough energy to make the entire universe simply ... disappear. It sounds like science fiction, but that's exactly what quantum physics reveals to us about the vacuum of space. Today, we're diving into one of the most unsettling and fascinating concepts in modern physics, the discovery that the vacuum isn't truly empty. We'll explore zero-point energy, the mysterious quantum fluctuations, completely redefine what nothing means in physics, and uncover one of the most terrifying ideas in cosmology, the possibility of a vacuum catastrophe that could erase our reality in a fraction of a second. Get ready to have your intuition about empty space completely transformed. Hello, cosmic explorers. Welcome back to Cosmic Frontiers, where we unravel the deepest mysteries of the universe. We're a community passionate about discoveries, and we're building an incredible journey together towards our first 1,000 members. For centuries, when we thought of a vacuum, we literally imagined absolute nothingness, a completely empty space, without matter, without energy, without absolutely anything. It was like imagining a perfectly clean box, where even the air had been removed. Aristotle even said that nature abhors a vacuum, believing that such a thing couldn't even exist. This classical view made perfect sense for our everyday experience. After all, when we use a vacuum cleaner, we're creating a region of low pressure, a relative vacuum. The more air we remove, the emptier the space becomes. Following this logic, a perfect vacuum would simply be the total absence of everything. But at the beginning of the 20th century, something extraordinary happened. Quantum mechanics began to reveal that our intuition about reality was completely wrong. And one of the most shocking discoveries was precisely about the nature of the vacuum. Imagine you're on a seemingly calm beach at night. At first glance, the sea looks perfectly smooth, like a black mirror. But if you look more closely, you'll notice small, constant ripples, a subtle movement that never stops. Quantum physics tells us that the vacuum is exactly like that, seemingly empty at first glance, but teeming with activity when we observe more closely. The revolutionary discovery responsible for this was Heisenberg's uncertainty principle. Proposed in 1927, Werner Heisenberg discovered that there's a fundamental limit to how much we can simultaneously know about certain properties of particles, such as position and momentum, or energy and time. But here's the fascinating detail. This principle doesn't just apply to the particles we can see, but to the very fabric of space-time. The uncertainty principle tells us that we cannot have absolute zero energy in any quantum system, not even in a vacuum. This means that even in the emptiest possible space, there must be a minimum amount of energy, called zero-point energy. It's as if the universe has a basic fee of energy that can never be reduced to zero. Think of it like a nightclub that's never completely empty. Even when all the customers leave, there's still background music, emergency lights, the ventilation system running. There's a minimum activity that never ceases. The quantum vacuum works similarly. There's an energetic background activity that is absolutely fundamental to the existence of reality. This zero-point energy manifests itself through what we call quantum fluctuations. Constantly, pairs of virtual particles are appearing and disappearing in the vacuum. It's as if space itself is bubbling with instantaneous creations and annihilations of matter and energy. To understand this better, imagine you're observing a perfectly still glass of water. On a macroscopic surface, it appears completely motionless. But if you could see at the molecular level, you'd see absolute chaos. Billions of molecules moving frantically, colliding, vibrating. Quantum fluctuations are exactly that, but happening at the most fundamental level of reality, where particles and antiparticles emerge from nothing and annihilate in incredibly tiny time intervals. But you might be asking, if these particles appear and disappear so quickly, how do we know they really exist? Wouldn't it just be a mathematical curiosity? The answer is no, and we have impressive experimental evidence. One of the most elegant proofs of the existence of quantum fluctuations is the Casimir effect. Discovered by Dutch physicist Hendrik Casimir in 1948, he predicted that if you placed two extremely close metallic plates in a vacuum, quantum fluctuations would exert a force, pushing the plates towards each other. It's as if quantum fluctuations were waves in the cosmic ocean. Between the plates, only waves of certain sizes can fit, while on the outside, waves of all sizes are present. This difference in the radiation pressure of the fluctuations pushes the plates together. In 1997, this effect was experimentally measured with incredible precision, confirming that quantum fluctuations are absolutely real. Another fascinating piece of evidence comes from Hawking radiation. Stephen Hawking demonstrated that near the event horizon of a black hole, quantum fluctuations can cause one particle of a virtual pair to escape, while the other falls into the black hole. The result? The black hole loses energy and gradually evaporates, emitting radiation. It's one of the most elegant discoveries in theoretical physics, connecting quantum mechanics, general relativity, and thermodynamics in a brilliant synthesis. Now, let's get to the point that will truly blow your mind. What does nothing mean in modern physics? The answer is that nothing simply doesn't exist in the way we imagined it. In classical physics, nothing would be the complete absence of everything: matter, energy, field, structure. It would literally be an absolute void. But quantum mechanics teaches us that this is impossible. Even when we remove all the matter and energy we can, the fundamental quantum fields and their inevitable fluctuations still remain. It's like trying to achieve absolute silence in a city. You can close the windows, wear ear protection, isolate the environment, but there will always be some background noise. The sound of your own heart, the distant hum of traffic, the almost imperceptible vibration of buildings. The quantum vacuum is this background noise of reality. We can't remove it because it's an intrinsic part of the universe's structure. But here's where things get truly unsettling. If the vacuum we know has this zero-point energy, is there an even lower energy state? According to some theoretical calculations, it's possible that our current vacuum isn't the lowest possible energy state. It could be that we're living in a false vacuum, a stable state, but not the most stable one possible. Lawrence Krauss, a renowned theoretical physicist, explains this with a brilliant analogy. Imagine a ball in a valley between mountains. The ball is stable where it is, but if someone gives it a strong enough push, it can roll into an even deeper valley. Our universe might be in this situation stable, but not in the state of absolute lowest energy. And here we arrive at the most terrifying concept in all of cosmology, the vacuum catastrophe, also known as vacuum decay. If we truly are in a false vacuum, there's a theoretical possibility of a transition to the true vacuum, an even lower energy state. Imagine you're in a comfortable house built on an unstable layer of ice. As long as the ice holds, everything is perfect. But if it cracks, the entire structure could collapse instantly. Vacuum decay would be exactly that, but on a cosmic scale. If a tiny region of space, the size of a proton, underwent this transition to the true vacuum, it would form a bubble that would expand at the speed of light, destroying everything in its path. The laws of physics as we know them would cease to apply inside this bubble. Atoms would disintegrate, fundamental forces would change, the very structure of space-time would be altered. The most disturbing part is that there would be no warning. The front of the bubble would travel exactly at the speed of light, so we could never see it coming. One moment we'd be here, the next we would simply cease to exist, replaced by a completely different form of reality. Frank Wilczek, Nobel laureate in physics, describes this as death par excellence. Not just the extinction of life, but the extinction of the very possibility of life as we know it. It would literally be the end of our reality. But before you panic, take a deep breath. First, this is highly speculative. We have no evidence that our vacuum is unstable. Second, even if it were possible, the timescales involved could be astronomical, much, much greater than the current age of the universe. And third, it could be that natural mechanisms prevent this transition. In fact, some physicists argue that the very fact we are here to contemplate this possibility suggests it's extremely unlikely. This is what we call the anthropic principle. If the vacuum were easily unstable, universes like ours simply wouldn't have time to develop enough complexity to produce conscious observers. Furthermore, recent calculations using data from the LHC particle accelerator suggests that our vacuum may be stable, or, at worst, metastable, with a lifespan far exceeding the age of the universe. We can sleep soundly, at least regarding this, but the mere theoretical possibility of the vacuum catastrophe makes us reflect on the fundamentally precarious nature of existence. We live in a reality that seems solid and reliable, but which may be just one particular configuration among infinite possibilities. And this leads us to an even deeper understanding of the vacuum. It's not just not empty, it could be the very source of everything that exists. Some cosmological theories suggest that the quantum fluctuations of the primordial vacuum were the seed of all the structures we see in the universe today. During cosmic inflation, in the first moments after the Big Bang, tiny quantum fluctuations were amplified to gigantic scales, becoming the density variations that eventually formed galaxies, stars, and planets. In other words, you, I, and everything we know may have literally emerged from nothing, or rather, from the intrinsic quantum properties of the vacuum. Alan Guth, the physicist who proposed the theory of inflation, describes this poetically. The universe may be the ultimate free lunch. All the energy and matter we observe may have emerged from the inherent fluctuations of space-time itself. This possibility connects us deeply with the cosmos. We are not just external observers of the universe. We are literally made of the same vacuum that permeates all space. The quantum fluctuations happening right now around you may be fundamentally identical to those that gave rise to the first cosmic structures. Recapping this fascinating journey, we discovered that the vacuum isn't empty, but teems with zero-point energy and quantum fluctuations. We learned that absolute nothing doesn't exist in quantum physics, and we explored the terrifying, but likely remote, possibility of a vacuum catastrophe that could rewrite reality instantly. These discoveries force us to rethink our relationship with the space around us. Every cubic centimeter of the universe is vibrating with invisible quantum activity. The empty space between the stars isn't a sterile desert, but a dynamic ocean of energetic possibilities. This makes me reflect. If even nothing is full of infinite potential, what does that say about our own existence? We are temporary emergences of a cosmic substrate that never rests, never stops creating and recreating reality in every quantum instant. Our consciousness, our ability to contemplate these mysteries, may be one of the most extraordinary manifestations of the fluctuations of the cosmic vacuum. Cosmic explorers, can you imagine anything more humbling and at the same time more grandiose? We are literally organized structures of the quantum vacuum, gaining self-awareness through our eyes and minds. Now, I want to hear from you. What aspect of these discoveries about the vacuum impressed you the most? The zero-point energy that permeates all space, the quantum fluctuations constantly creating and destroying particles, or the theoretical possibility of a vacuum catastrophe? Leave your thoughts in the comments. I love reading our community's unique perspectives on these profound topics. And since we talked about the nothing that is actually full of possibilities, what other mysteries of the universe would you like to explore together? Black holes, dark matter, the nature of time, cosmic explorers. What frontier of physics do you want me to talk about in the next video? Leave your suggestions in the comments. You are the ones who guide our journey of discoveries. We're on an incredible journey towards 1,000 cosmic explorers, and each one of you is fundamental to this adventure. If this video expanded your understanding of the deep nature of reality, join our crew by clicking subscribe. Like this video if it transformed your view of the void of space, and share it with someone who is also fascinated by the paradoxes and mysteries of the universe. In the next video, we'll explore another concept that challenges our intuition: how time may not be what we think it is, and why some physicists believe it may be an emergent illusion. Until then, keep looking up at the sky and remember, even the seemingly empty space between the stars is pulsing with the infinite possibilities of the quantum cosmos.